Okay, we are looking at mass spectrometer examples. And as we take a look through here, there are four major parts to a mass spectrometer. The first one is the ionization chamber, or the ion source, where a vaporized sample is heated up. And then will be accelerated. The second area is your velocity selector, where you use an electric and magnetic field to make sure that the charged particle is in fact deflecting, is the exact velocity, and you can select it. The third one is an ion separator. This is part of the detection chamber, where a magnetic field is going to cause the ion to move into a circle, and there's a detector at the end in order to make sure that, hey, yes, this is in fact where we are getting those materials. So let's take a look at our first example. Our first example has find the velocity of a lithium-7 ion if it is accelerated by a potential difference of 20,000 volts. Now, lithium-7 is going to have 7 atomic mass units, so 7 times 1.67 times 10 to the negative 27, which gets us a mass of 1.169 times 10 to the negative 26 kilograms. It will also have a charge. Lithium has a charge of +1, which means 1.6 times 10 to the negative 19 coulombs. And so in this case here, we want to find the velocity. It's being heated up. It's accelerated by a potential difference of 20,000 volts. And that is happening in this ion source area. Okay, the voltage is going to be equal to the change in energy divided by the charge, or the voltage times the charge is going to be equal to the change in energy. Now, because the change in energy, the change in energy is basically the final energy minus the initial energy, but we are assuming that they are coming from rest in this area, means that we can essentially just go VQ is equal to 1/2 mv squared, where this velocity is your final velocity. So isolating V, or the velocity, will get you this using 2 times the voltage times the charge divided by the mass which has been given. We should find a velocity of 7.40 times 10 to the 5 meters per second. Alright, we are going to get you to try this one, finding the velocity of a lithium-6 ion accelerated by a potential difference of 10,200 volts. Pause the video, try this out, see if your answer matches. Okay, so taking a look at the answer here, you should have wound up with a 5.7 times 10 to the 5 meters per second. Lithium-6 contains 6 atomic mass units, or 3 protons, 3 neutrons. The voltage and charge are here. And same procedure. We're taking the change in energy, where we can assume that that change in energy is all final, assuming that it started from rest. V is equal to square root 2 VQ over R, where that is the voltage. We're looking for the velocity, gets you the 5.7 times 10 to the 5. Next example is taking a look at the velocity selector. Now, in this particular area, you've got equal electric and magnetic fields. So the electric field and the magnetic field are working equal to each other in order to have this particle to go undeflected. Anything moving slightly slower or faster will deflect off path, meaning only those particular things at a particular velocity will make it through. Now in this case, the force electric is equal to the electric field strength times the charge, and the magnetic is QVB. The charge, you'll notice, cancels out. The electric field strength divided by the magnetic field strength gets you the velocity. We've been given the electric field strength and the magnetic field strength, so dividing those two will get you 5.0 times 10 to the 5 meters per second. So that's just, again, taking 3.6 times 10 to the 5 newtons per coulomb, dividing it by 0.72 Teslas. Okay, this next one is another one for you to try. Pause the video, see if your answer matches the one that I've got here. We've got a lithium 6 ion passing through at 5.7 times 10 to the 5 meters per second. The magnetic field there is 1.2 Teslas, and the plates are 3 centimeters apart, and we're just trying to find what voltage we have applied here. And as you take a look here, again, the electric and magnetic field are equal to each other, but the electric field, we're having to take that voltage divided by the distance between the plates. Charge cancels out again, leaving you with the voltage is equal to the velocity times the magnetic field strength times the distance between the plates, which should get you 2.05 times 10 to the 4 volts. Our third example comes from this region where ions are separated and detected. So in this case here, a magnetic field is actually moving the ions into an arc. Now in this case, we want to know what the mass of a particular ion is. We know that is traveling at 4 times 10 to the 7 meters per second and has a radius of 0.487 meters or 48.7 centimeters due to a 6 Tesla magnetic field. The centripetal force, what's causing it to move in a circle, is that magnetic force. So mv squared over r is equal to qvb, where one of the velocities is going to cancel out. We are looking for the mass, so we need to isolate mass, which is going to get you QBR over the velocity. All of these are numbers that we have in the fact that we know that, I did not put it on here. We're going to assume it's the same ion, 1.6 times 10 to the negative 19 coulombs charged, as if this were a lithium ion. Now plugging these numbers in, we're looking for the mass. It's 1.6 times 10 to the negative 19 coulombs multiplied by 6.00 Teslas, a radius of 0.487 meters, all divided by the velocity of 4.00 times 10 to the 7 meters per second. And what that's going to result in is a mass of 1.17 times 10 to the negative 26 kilograms, which is approximately the same as having 7 atomic mass units. So this is, in fact, lithium-7. Here's an example for you to try. We want to find out what the radius of curvature is of a lithium-6 ion traveling at 5.7 meters per second as it enters a magnetic field of 5.3 Teslas. Pause the video, try this one, see if your answer matches. All right, and when you do this, again, we're looking at that velocity mass selector where we're separating the ions and detecting them. The ions are moving in a circle, so the centripetal force is equal to the magnetic force, or mv squared over r is equal to qvb. Isolating the radius, given all the data we've got, gives you a value of 6.7 times 10 to the negative 3. We have one more example here. Potential difference of 1.66 times 10 to the 4 volts accelerates a positively charged ion of 1.6 times 10 to the negative 19 coulombs from rest. It enters into a magnetic field perpendicular to a motion and then curves as it experiences a force of 5.27 times 10 to the negative 15 newtons. Well, we're given a hint here is to solve for the velocity in the ion separation region first. So this is kind of working backwards. The centripetal force is equal to that magnetic force, or in fact, we can say that that centripetal force of 5.27 times 10 to the negative 15 newtons is equal to QVB. And we're solving for velocity. We've got the charge. It's a lithium ion. And it's a positively charged 1.6 times 10 to the 19 coulombs. We've been given the mass, so we're just going to divide these both out in order to first of all get a velocity. And when we type in those numbers, we should get 1.03 times 10 to the 6 meters per second for the velocity. Now we can figure out what the mass of the ion is, given the fact that the change in energy in that source region is still going to be equal to VQ. Formula sheet actually has delta E over Q is equal to the voltage. It's just manipulated. It's starting from rest, as we're told, which means 1/2 mv squared is equal to VQ. So M is going to be equal to 2 voltage multiplied by charge divided by the velocity squared. We have all these numbers, and the final result is 5 times 10 to the negative 27 kilograms, which is the equivalent of about 3 atomic mass units. And given the fact that this is a positively charged ion, we're probably thinking that this is hydrogen 3. One last one for you to try. Here, doubly charged ions, mass of 4 times 10 to the negative 26 kilograms, pass undeflected. The selector has a magnetic field of 0.28 teslas in an electric field of 4 times 10 to the 5 volts per meter. And so it's undeflected in this area of the velocity sectors. They travel into the separator, deflecting with a path here. And we want to know what is the magnetic field strength in the ion separation unit. Pause the video, check this out, see if your answer matches. And you should have wound up with an answer of 1.2 teslas, because again the electric and magnetic field are together in the velocity selector region. Means you can find the velocity of these ions fairly precisely, which then, as it deflects into a circle, we've got it through this radius here of 5 times 10 to the negative 2 meters, or 5 centimeters, which we plug into here, gets us the 1.2 teslas. Thanks for watching.